Hello class, welcome to section 13.3. Moving into permutations and combinations, obviously, these are special ways of how we can decide how to order things, how to order objects. Would be like seating, objects on a shelf, objects in a row. Knowing how many ways we can order something is what permutations and combinations are about. So, let's start out with the problem. You're planning a wedding and you want 5 people to sit at the table next to the bride and groom. So, some are family, so seating choice is of course important. How many ways are there to do this? So I want to know how many ways can I sit 5 people in such a way that I have taken into account order. The solution is each person takes a spot. So obviously, our fundamental counting principle is a little altered. Normally, right, it means for each choice that we have that many choices times the next one. But of course, in this time, if each person is taking up a spot, we're losing one person each time. So it's 5 times 4 times 3 and so on. 120 ways. This is called a permutation. Permutation is an order arrangement where we can't use an item more than one, and the order is significant, and that's important. That's the distinction with a permutation and that against a combination. So permutation's order is important. And for example, if there were 7 people, we do 7 times 6 times 5 and so on to get 5,040 ways. And this order, this sequence, starting with a number, multiplying one less, is called a factorial. And it's expressed with an exclamation mark, which you'll see in a minute. So I said, this is different from a combination, where we arrange items where, again, no item is used more than once, and order makes no difference this time. So again, permutation is where order is significant, a combination order is not significant. For example, in permutation, like I said, choosing a wedding party where, since it's family, order is significant. You most likely wouldn't put the cousin of the bride or groom closest. You put, the opposite of the parents. Combination is something as trivial as choosing flavors of an ice cream, or I need 2 pairs of black socks from the 4 that I own. So let's look at some more examples. Here we go. So like I said, a factorial says if n is a positive integer, then n, the exclamation mark, and so we say factorial, is the product of n times n minus 1 times n minus 2, and that whole idea where we're going down the line, taking away 1 each time, all the way down to 1. Where 0 factorial is always considered 1. So for example, 6 factorial divided by 4 factorial. When you divide, instead of actually putting that into your calculator, doing 6 times 5 and so on, instead, use this little trick that I'm illustrating here. I'm writing out all my multiplication facts. So 6 times 5 and so on, 4 times 3 and so on. Now, since it's all multiplication, I can cancel out my common terms. In other words, my 4, my 3s, my 2s, my 1s can cancel out. Which means I'm only left with my 6 times 5, so it's 30. So if you ever divide factorials, this is the more efficient way of doing it, to save yourself some work. So again, 31 factorial over 28 factorial, of course, that'd be 2 very, very large numbers. If you try putting 31 factorial into your calculator, it may not be able to do it. So instead we say, let's just take 31 out so I can get to 28. And then we know that beyond 28, in the numerator, will match everything in the denominator, because the denominator starts at 28 itself. It goes to 27 and so on. So everything from 28 down cancels out, which means we're left with 30 times 31 times 29 for 26,970. So again, this is the way factorials work. And factorials are used to do permutations and combinations. So if there are 14 players on a baseball team available for a starting lineup, how many ways are there for creating a starting lineup of 9 players? This is where we use our permutations. So we say permutations of n things taken r at a time. So n is the total number of things that we have in whatever we're considering. R is obviously the amount that are taken at a particular time. So this is our setup for permutations. Now one thing to keep in mind, the style that you see here, little n, p, little r, this is an older style notation. The book tends to use this. It tends to use permutation with p, and then the total number, comma, then the amount that I'm taking at a time. This is the order, and the same with combinations that the book chooses. So just to forewarn you about the way both work. Either way, it doesn't matter. The setup is the same. My 14 is my n, the total number of people we're considering this time. R is the number that we're choosing at a time, so that's 9. So we do 14 factorial over 14 minus 9 factorial. That becomes 5 factorial. And again, instead of doing all that multiplication, just say, well, 14, if I keep multiplying down, cuts off at, when it gets to 5, everything after that will cancel out. So I'm only multiplying it from 14 down to 6. That gives me 726 million. So again, the reason I only multiplied what you see is that if everything after 6, 5 times 4 times 3 and so on, is going to cancel out with a 5, 4, 3, 2, and 1 in the denominator, since the denominator is 5 factorial. So these are the numbers that are left over after canceling out. A board of directors needs to assign a president, vice president, and treasurer. How many ways are there to do this? So again, with permutations, first of all, we identified that order is important because we're talking about a president, vice president, treasurer. There is significance to the order chosen. So we know we're doing permutations. How many possibilities do we have? It's going to be 8. 8 directors that we're choosing from. How many are we taking at a time? We're taking 3, 1 for each position. N is 8, R is 3. Plug it into my formula, and it gives me 336. So permutations of duplicate terms. So permutations of, again, n items where p are identical, q are identical, and so on. It means we have repeat values. Let me show you. How many ways can you rearrange the word osmosis, or excuse me, the letters in osmosis? So this is what I mean by p repeated, q repeated, and so on. Our total number that we're choosing from is 7. 3 S's, 2 O's, 1 M, 1 I. So instead, I have 7 over 3 factorial times 2 factorial. Now I didn't put in 1 factorials in there because it wouldn't have made a difference. But I'm doing the factorial of each of the repeat parts. And when you do your math, you'll end up with 420. And again, what happens here is my 2 and my 1. Let me draw this out just in case there's any questions. My 2 here cancels, my 1 cancels, and this 3 cancels with this 3. That's how I get this set up. And as I said, it's 420. Now, combinations. As you can see, written the same way, just with a C instead of a P. And, similar to the way permutations are often written in this book, combination is written C, then in parentheses, N, comma, R. Again, means the same thing. And you notice the difference. We have N factorial on top. In the denominator, we have N minus R factorial, but then we also have R factorial repeated. That last R factorial is the difference between combinations and permutations. An 8-person board has to create a 4-person committee. How many committees could be formed this way? So now notice I didn't say anything about significance of the order, of the placement. It's 4 people from 8, that's a combination. N is 8, R is 4. Toss it into my formula. End up giving me 70. To win the New York State Lottery, you must correctly select 6 numbers from 59 possibilities. Order is irrelevant. How many selections are possible? So again, order is not important. We're choosing a small amount from a larger amount. How many ways can we arrange it? That's a cue for combinations. That's a cue for combination or permutations. And then the fact that the order is irrelevant means it's a combination. N is 59, R is 6. This is my formula, 59 factorial over 59 minus 6 factorial times 6 factorial. So that leaves me with 53 times 6 factorial. When you do your math, end up with about 45 million ways of choosing. So again, the main thing is we have permutations where order is significant and combinations where order is not significant. So this concludes our lesson for section 13.3. As always, if you have any questions, feel free to contact me and have a good day.